Alright, so welcome back. We are moving on to our pizza ontology and we are going to create some more interesting class definitions, and on those we are going to perform some more interesting classifications. And this time we are moving on from, we've already used existential restrictions, and now we are going to use some universal restrictions which we know are denoted using this symbol in description logics. Universal restrictions imply that, so for instance, if there is a condition that for all has topping mozzarella topping, it means that the only toppings this particular pizza may have is mozzarella topping, and this property has topping does not participate in any other individuals or any other value types. So to understand this further, let's do exercise number 31, and we are going to create a subclass of pizza called vegetarian pizza, right? And for vegetarian pizza, we would like to classify its toppings to specifically vegetarian toppings. And so we'll create the subclass, and we're going to create a property restriction. There are two ways to do this. We could select has topping, and we either want to say it has cheese topping or a vegetarian. So let's say select vegetable topping, and we could say in this case we'll be using the restriction type universal, which is for only. So when we add this, here we are saying that it has topping only a vegetable topping. I'm going to modify this. I'm going to go to my class expression, and I'm going to try and say here by using my union operator. And what I want to say is that a vegetarian pizza is a class that has topping only vegetable topping or cheese topping, right? And I could give it parentheses to make it clear, right? So this is what my class definition looks like for now. And as you notice, this is the keyword only indicates a universal restriction, right? So what this means is that if something is a member of this class, which is the vegetarian pizza, it is necessary for it to be kind of pizza, and it is also necessary for it to only have toppings that are kinds of cheese or kinds of vegetable topping, right? So the only has topping relationships the individuals which are member of this class have must be individuals that are either members of cheese or vegetable topping. Now, a common mistake in this case is to say, notice what would happen if I were to say, instead of or, I were to say and here. This would completely change the definition of this vegetarian pizza, right? This is incorrect, as we've already seen that our cheese and vegetable toppings would never intersect. So the keyword and indicates that something is a cheese topping and vegetable topping at the same time. So we simply cannot do this. So I'm going to modify this back to a or, right? And it is also possible that we may create this definition in a different manner. Let's say I say has topping only a vegetable topping, and then I add another restriction and I say has topping only cheese topping, right? Once again, this sort of a class description for this class definition would be wrong. When you use multiple restrictions, the complete description is taken to be the intersection of those restrictions. And this would again imply that we are trying to have a restriction with a filler that has the intersection of vegetable and cheese, which is once again never possible, right? So this would again be incorrect. That is why I'll remove it, and modify my restriction back to the correct version, which is vegetable or cheese topping, right? And that's what I want my vegetarian pizza to be defined as. Now notice we are creating necessary conditions here. We have not yet defined as our and vegetarian pizza class as a defined class. So we can convert this by as we did earlier, we can use our convert to defined class tool here to shift these conditions to our necessary and sufficient conditions. So this completes our exercise 32. Now what we would like to do is to perform some reasoning now that we have a defined class. And if you remember, we know that the reasoner can only classify members of defined classes. For primitive classes, reasoning of this nature may not be or cannot be done in almost all cases, right? So what we want is to use the reasoner to automatically compute the superclass and the subclass relationship. And if you remember, we created some named classes, Margherita Pizza and Soho Pizza. And if you notice, Margherita Pizza has only tomato and mozzarella, it means vegetable and cheese. And Soho Pizza again also has veggie, cheese, so only veggie and cheese. So we would expect that once we run the reasoner, now that we have a vegetarian pizza defined class which has topping only cheese or vegetable, we would expect to see Margherita and Soho Pizza classified as subclasses of vegetarian pizza. So let's try and run that to see if this works. I'm going to stop the reasoner first and then start. And when I look at my class hierarchy, that is not the case. My vegetarian pizza, incidentally, has not seen any classification. I do have classifications for my cheesy pizza as we saw earlier, but not in the case of vegetarian pizza. And the reason for this is, as we have been discussing in class, it is the open world assumption. And it is also referred to as the open world reasoning. And once again, we cannot assume something until it is explicitly stated. That we cannot assume that something doesn't exist until it is explicitly stated that it does not exist. In other words, because something hasn't been stated to be true, it cannot be assumed to be false, right? So we can say that the knowledge is out there, it just hasn't been added to the knowledge base. So just because for our Margherita pizza we see that it has some mozzarella topping and it has some tomato topping, it doesn't mean that these are the only toppings it has, or at least we have not stated that to be the case, right? So it needs to be explicitly stated that these are the only toppings it has. Otherwise, this information is not sufficient for an inference to be made that Margherita pizza is actually a vegetarian pizza. And how we do this in our protege is by adding a closure axiom. And if you go back to your tutorial, closure axiom is explained in this section, which is section number 4.13.1, right? So a closure axiom is a restriction that gives a property a filler by saying that these are the only possible fillers it has, or these are the only possible values it has, and this restriction can be asserted by creating a union of the fillers that exist in the existential restrictions. So for example, if the Margherita pizza has two existential restrictions, one with mozzarella, one with tomato, so we would need to add a closure axiom that would say that it only has toppings which are the union of mozzarella and tomato, right? So how do we do that? There is more than one way of doing so. We could do the simple restriction editor approach. For instance, I would go to my add subclass of description and I would say has topping only, right? So has topping only. I'm going to add brackets, mozzarella, and no, or tomato, right? So I am giving a union of the two types that are already asserted using the existential restriction. And I'm going to press OK. So you can notice now my margherita pizza has topping tomato, margherita pizza has topping some mozzarella. And now in addition to these two, I'm saying that it has at least one tomato topping, it has at least one mozzarella topping. But now the only toppings it will have is either mozzarella or tomato, nothing beyond these two. So this is really, we're closing the world of assumptions here. Now in this case, we no longer expect that there is a possibility of some additional information which may not be asserted here, right? So we've tried to be as explicit as possible here. And let's do another closure axiom exercise. In this case, I'm going to add um, a closure axiom for my Soho pizza. So I'm going to add has topping. All right. So I'm just going to modify this. So mozzarella and tomato are already there. I'm going to say or olive or parmesan, right? I'm going to close. So basically, if you notice that this closure axiom is simply a union of the uh, others which have been asserted using the existential quantifier, right? Another way we can add a closure axiom is by selecting one of these axioms or restrictions, right clicking and creating a closure axiom. So if you notice, this is a shortcut approach. It has simply added a closure axiom by selecting the values from the existential restrictions. And we could do the same for American hot pizza. I'm going to add a closure axiom, right? So now having done this, now let's see what happens when we run the reasoner again, right? So let's see. So you notice that margherita pizza and Soho pizza have been classified as a vegetarian pizza. And this was what we expected initially, but we were unable to do so because of the missing closure axiom. So the closure axiom is a really important element in creating class definitions that need that need to be exclusively or explicitly specified for closure. So with this, we have completed until exercise number 38. We could also visualize the class hierarchy using the OwlWisp plugin. You would notice that primitive classes have the color yellow and the vegetarian and the cheesy pizza, which are the defined classes, have a different color. And the OwlWisp plugin lets you view the asserted hierarchy versus the inferred hierarchy visually. And as you can clearly notice that there are multiple inferences that have taken place. Soho pizza was initially a named pizza. It's classified both as a cheesy pizza and vegetarian pizza. And similarly for margherita pizza as well. And the American hot pizza and the American pizza are classified as the subclasses of cheesy pizzas. Next, we will move to value partitions in the next tutorial.